So what we're interested in looking at is how we multiply vectors together. So you guys are all familiar with multiplication. If I write something like 3 times 4, we've got two scalars that we're multiplying together. Now, how can we think of multiplication of two scalars together? You know, way back in grade 3 or something like that, you said, okay, well, I got 3 times 4. This is like 4 plus 4 plus 4 equals 12. Multiplication is repeated addition. And this makes a lot of sense if what we're thinking about is scalar multiplication of a vector, okay, like we did in Unit 1-2. If we had a vector that was vector v, and we said, okay, we want to multiply it by a scalar, 3v, it was like taking 3 vector v's and adding them one after the other. Okay, so this is repeated addition again. And then our result was, the vector sum of all 3 of these vectors. But now we're looking at multiplying vectors. So we've got something like a vector A and a vector B, okay, and we want to multiply them together. And you're probably thinking, okay, well, this vector here, this vector A, this vector B, they both have magnitude and direction. It's pretty clear that I don't think it would be surprising if I told you what we want to do is we want to multiply the magnitudes together. So we want to do something that is going to be magnitude A times the magnitude of B. That would be really consistent with what we did up here with scalar multiplication. What do we do with the directions? Okay? And that's the only hard part of vector multiplication, dot product and the cross product, is how do we treat the direction component of these vectors, which are integral to the vectors. We can't just get rid of it. We've got to do something with it. Okay? And that's the difference between these two forms of vector multiplication. The dot product and the cross product is how they handle this directional component that is associated with these vectors. So what we're going to cover today is the dot product. Okay? So once again, dot product, we are multiplying 2 vectors. And the dot product is often called the scalar product because the result of multiplying 2 vectors with the dot product is not another vector, it's actually a scalar. So we should just note that the result is a scalar. And if the result is a scalar, that kind of suggests that we're going to get rid of a lot of this vector, this directional information. Okay? And that's really what the dot product does. When we're doing the dot product, to put it into words here, we kind of take the parts of the 2 vectors. So take parts of our 2 vectors that are in the same direction. Okay, and multiply. Okay, so this is how the dot product deals with the directional information. It says, okay, well, we've got 2 vectors, they point in different directions. What would happen if they pointed in the same direction? Let's just take the aspect of them that points in the same direction, and we'll do the multiplication using those. And hopefully by the end of this, you'll sort of see what I mean by that. Okay, so here is an example, okay? We want to find A dot B, okay? A, the dot there in the middle, means that we are going to do the dot product of our 2 vectors. And we've got vector A here, magnitude is 120. We've got vector B down here at the bottom, magnitude is 100. I've placed them tail to tail, and the angle between them is 60 degrees. What if we wanted to find sort of the component of A that points in the same direction as vector B? Okay. We can do that using trigonometry. We can say, okay, we can break vector A into its 2 components. One component is going to point in the same direction as B. The other component is going to point perpendicular to B. And we can use trigonometry to figure out what these two components are. So this component down here, okay, the one that we actually want there is going to be, let's see, it's the adjacent angle over the hypotenuse. So this thing right down here is going to be magnitude of A times cosine of the angle between them. Okay. Theta is the angle between. Okay. And then we want to multiply it by B. So A dot B, okay, instead of doing the dot product, we'll say, okay, let's just take the part of A that is in the same direction of B. That's going to be magnitude of A cos theta, and then multiply that by the magnitude of B. And I'm just going to rewrite this as magnitude A, magnitude B, cos theta. Okay? That right there is the definition of the dot product. Okay? Magnitude A, magnitude B, cosine of the angle between them. Okay, so in this case, all we need to do is take our magnitude of A, 120, our magnitude of B, 100, cosine of the angle between them, which is 60 degrees, and punch this into our calculator and work out what it is. Okay. This is going to work out to be 6,000, I guess. Okay. Our answer is just a number, 6,000. It's a scalar, hence scalar multiplication. Okay. So this is basically the way of doing the dot product geometrically. So we'll just sort of summarize here. Our geometric interpretation of the dot product is, if we want to do the dot product of A dot B, it's going to be magnitude of A times the magnitude of B times the cosine theta. Where theta is the angle between the two vectors. So we use this form of the dot product when we're given two geometric vectors. We're told the magnitudes and how they're oriented relative to each other. So we're given magnitudes and an angle. Okay. So this is the kind of thing that would have been useful in Unit 1-2 when we were treating all of our vectors as arrows with a length in a specific direction. What about in Unit 3-4 here, where we've started treating our vectors not as arrows, but as these algebraic ordered pair kind of notation things? There's another way of doing the dot product that is sort of the algebraic way of doing this. Okay? So, any questions about this, about what we're doing here? Okay. All right. Let's do it like this. We'll just say algebraic notation. Okay. Again, we're still just doing the dot product here. So let's say we have two vectors, u and v. Okay. And we'll represent them as ordered pairs, or we can do ordered triples, actually. They can be three-dimensional vectors. So the u has components u1, u2, and u3. V has components v1, v2, and v3. And we want to do u dot v. Okay. the dot product here, what we're going to do is we're going to take our two x components, u1 and v1, and we're going to multiply them together. u1, v1. And this is just straight scalar multiplication here. So I'll just put brackets around it like this. u1 times v1. And to this, we are going to add u2 times v2. And to that, we're going to add u3 times v3. Okay. So we're picking out the components that point in the same direction. Our x components are all pointing in the x direction. Our y components are all pointing in the y direction. Our z components are all pointing in the z direction. So we multiply the components that are all pointing in the same direction. Okay? And then we add them up. So this is pretty simple to do. Okay? If we want to find our dot product, we're given two vectors here. A is -1, 5, and B is 3, 2. And we want to find A dot B. Okay. We are just going to take our two x components, -1 and 3, multiply them together. To this, we are going to add our two y components multiplied together. 5 times 2. Doing the first set of first multiplication, -1 times 3 gives us -3. 5 times 2 gives us 10. Our final answer is going to be -3 plus 10, which is 7. So our final answer here is a scalar, just like we would expect with scalar multiplication. Okay. So, two ways of doing the dot product. Geometric, algebraic. Okay. Good on this? Okay. So the next example we're going to do, we're going to use both forms of this, okay, at the same time. Okay. A little bit of an application here. Good? Okay. I'll just give you a second here to copy this down. So we want to find the angle between two vectors. Vector v is 1, -2, 3, and vector u is 4, 2, -1. And what we're going to use here is we're going to use both forms of the dot product. We're going to use the fact that our algebraic form, u dot v, okay, is equal to the magnitude of u times the magnitude of v times the cos of the angle between them. And it's the cosine of the angle between them that we're trying to find here. Okay? So we want to figure out what everything else is in this expression and then rearrange it to solve for cos theta. So let's start by figuring out the left-hand side here, u dot v. Well, if we want to find u dot v, we're given two algebraic vectors here, 1, -2, 3, and 4, 2, -1. So we can just do the dot product of those algebraic vectors. 1, -2, 3, dotted with 4, 2, -1. Okay, and we can work out what this is. X times x is 1 times 4, which is just going to be 4, plus -2 times 2, which is -4, our two y components, and then 3 times -1, -3 for our z components, and then we just add them all up to get -3. So we figured out the left-hand side here. What do we have left to figure out? Well, we need the magnitude of u and the magnitude of v. So how do we find the magnitude of a vector? Anybody recall? Well, if it was in 2 dimensions, we used Pythagorean theorem. So in 3 dimensions, we just extended this Pythagorean theorem to 3 dimensions. We take our x component squared plus our y component squared plus our z component squared, and take the square root of that whole thing. So we do 4 squared, 16, plus 2 squared, 20, plus 9 gives us, 16 plus 1, 2, 3. What have I done there? 4, 2. Yep, 20, 29. 29? Yeah? Okay. I sound skeptical because for some reason in my notes I wrote 21. Who knows? So, magnitude of v, we do the same thing. Square root of 1 squared. Oh wait, v is, yep, 1, 2, okay, 1 squared plus negative 2 squared plus 3 squared. No, that's, oh.
Yeah. It is 21. You got some straight.
What are you going to do? So here we are trying to fix the disaster that we've gotten ourselves into here. So this time around, I'm going to write u and v in the correct order here. And I actually did this to show you an important point. It doesn't matter what order we do the dot product in, the answer is still going to be the same. So I can do u dot v or I can do v dot u. I'm still going to end up with the same answer. So we'll go through the dot product again. 4 times 1 is 4. 2 times negative 2 is negative 4. Negative 3 times 3 is negative 3. Lo and behold, we still have negative 3 for our dot product. Okay, magnitude of u, as I said before, we are going to add these things up using the formula. U is 4, 2, negative 1, so 4 squared plus 2 squared plus negative 1 squared. Taking the square root of that gets us root 21, just like I had in my notes. Imagine that. Same thing for v. Magnitude v, we are going to take the square root of 1 squared plus negative 2 squared plus 3 squared. We do this addition and we get root 14. Okay. Am I back on track here? Yes? This looks like good math? Bad math? No? Okay. All right. So we've got everything filled in that we need here. We just want to rearrange this thing for cosine theta. So cosine theta is going to be u dot v divided by magnitude u, magnitude v, okay, from that expression we had up at the top. I think you see where we're going here. We just sub in what we found here. So u dot v is negative 3. On the bottom, we're going to have root 21 and root 14. Punch this into our calculator and take the inverse cosine, and we find out that our angle theta here is 100 degrees. And there we are. That's the angle between those two vectors.